Hey guys, so in this video I want to talk about acceleration as well as introduce you to the 3 to 4 equations of acceleration. That's going to be the foundation for most of our motion problems, also known as kinematic problems. So let's get on it. Acceleration is given by the letter A, and it's defined as change in velocity over change in time. Velocity is a vector, acceleration is a vector. Change in velocity, the delta notation is v final minus v initial, and divided by time. Velocity is meters per second, and time is seconds. So if you combine this, you get meters per second squared, and you should absolutely remember that that's what the units are. Acceleration is always a vector, always a vector. Let me talk about that for a little bit. If you remember, when we're measuring how much something moves, there are two words. There is distance and displacement. One is a scalar, the other one is a vector. And if I'm measuring how fast something moves, there are also two words, speed and velocity. Now, these two guys are associated with each other, and velocity is defined in terms of delta x. Now, in terms of acceleration, there's only acceleration and there's only a vector. That's what I mean by always a vector. There's no scalar equivalent of acceleration like what you have with velocity and displacement delta x. Acceleration is always a vector. Now, one thing that people that can be confusing and people will get confused with sometimes is that the positive, if you have a positive acceleration, it doesn't mean necessarily that you're speeding up. What it means instead is that your velocity is becoming more positive. And I need you to remember that. Positive acceleration means your velocity is becoming more positive. Like what you see with distance and displacement and speed and velocity, in everyday language, we use these words kind of interchangeably, loosely, just like how in everyday language, acceleration, if you're accelerating, it usually means that you're speeding up. But in physics, we have to be careful with these because it's a little bit different. Acceleration has to do with velocity, not with speed. Okay? So speeding up means that you're becoming faster. And it does not necessarily mean that your velocity is your velocity is becoming more positive. It doesn't necessarily mean that you have a positive acceleration. And slowing down, if you're becoming slower, it means that your speed is going down, not the velocity. Remember, velocity is a vector. So velocity is comprised of, because it's a vector, it's a magnitude, whatever the number is, and that number, magnitude, is speed and a direction. Okay? So if your speed changes, you could change one without changing the other, basically. Let me jump into showing you some of this stuff right away. So, for example, if I'm going from -3 in terms of velocity, this is a number line showing the velocity, and if I go to the right of the number line, I'm becoming more positive, so my velocity is increasing, or becoming more positive, I should say, and my acceleration is positive. Let's say I go from -3 meters per second to -1 meters per second. What's happening here? I'm going to the right of this line, so my acceleration is positive. However, my speed is decreasing. Why? Because speed is a scalar. It doesn't care about signs. It's just a number. I'm going from 3 to 1. Ignore the signs. And obviously 3 to 1, you're getting smaller. So your speed is decreasing. So you are slowing down, but you have a positive acceleration, right? Weird. So anyway, there's all these kind of different things. So I told you that acceleration grows to the right, while speed grows this way. This, if you're going from 0 to the right, your speed is growing. If you're going from 0 to the left, your speed is growing. As long as the number, forget the sign, if the number is getting bigger. The flip of that is if you're going towards 0, from the left or from the right, that means your speed is going down. You're becoming slower. Okay? Here you are becoming faster. So again, speed and velocity, different things. Faster and positive acceleration, different things. This is kind of tricky, but I want to get this out of the way now rather than you be confused for some portion of the course. The best way to do this is just with examples. Let's do this one. I'll do the first one. I want you guys to try the second and the third. So I'm going from +2 to -5. Always draw as much as possible, right? So 0, +2, -5, a little velocity number line, if you will. And I'm going, my initial is +2, and my final is -5. So I hope you see here that since I'm going to the left, my acceleration is negative, right? And what about my speed? Look at the number. I'm going from 2 to 5. It doesn't matter that it's positive, negative. That number is increasing. Again, negative acceleration, but my speed is increasing, okay? So, and by the way, as you're going from 2 to 0, your speed is actually decreasing. And then from 0 to 5, your speed is increasing. But what matters is not what happens sort of in between. You just look at the very beginning and at the very end. And you went from 2 to 5, your speed is increasing. Okay? That's the first one. I'm going to do the second one over here. I'm just kind of making some space, and then we'll do the third one here. So B, I go from -2 to -5. Let me draw that. -5, -2, 0. I'm going from -2 to -5. -2 to -5. Notice that the numbers are the same. I just kind of messed around with the signs a little bit to see how this works. -2 to -5, I'm going to the left in the velocity line, so my acceleration again is negative. And my number is going from 2 to 5, forget the signs, so my speed is again increasing. So it's, you know, effectively the same answers, even though the numbers are a little bit different. C, -5 to -2, let me draw that. Here's -5, -2, here's 0. And -5 to -2 goes like this. I am going to the right, so I'm becoming more positive. You're getting more and more towards the positive, so my acceleration is positive. My speed, however, is decreasing because I'm going from a 5 to a 2. The number, forget the sign, the number is becoming smaller, okay? So hopefully that makes sense. There's some other stuff with this that I'm leaving to talk about, for us to talk about later. But for now, I need you to remember that a positive acceleration has to do with becoming more positive, not necessarily with speeding up. And that speeding up, slowing down actually has to do with speed. That's the first half of the video. Now we're going to get into the equation part, show you guys some equations. So remember, we talked about this. If your acceleration is 0, then you have a constant velocity, which might be an average velocity. And then we have this equation. This is the only equation you have, right? You have one equation. Now, I showed you that there's sort of a, you can write this equation in a different way, and it looks like this. X, move some stuff around, x equals x initial plus vt. And I told you the reason this is relevant, this equation, is because we're going to use these in some problems. So I'm going to call this the position equation. And it's really the same equation, two versions, but that's if your A is 0. If your A is not 0, you're going to have 4 equations of motion, and now you're going to have to get into the whole deal of having to pick the right equation. The reason why there's a star here is because some professors will give you 3, some professors will give you 4. If the professor gives you 4, you can use all 4. If the professor only gives you 3 equations, that 4th equation you may or may not be able to use. If your professor is very picky about you only using stuff he gives you, then you have to stay away from the 4th equation, that extra 4th equation. If he doesn't care, then you can use it, okay? So that's why this 4th equation, when I list it here, I'm going to call it the extra equation, okay? And we'll get to that in a little bit. So I call these the equation of motion, but they're also referred to as kinematics equation, right? Kinematics is just the study of motion. That's the fancy physics word. Another name for these is they are the UAM equations, and it just means uniformly accelerated motion. In all of these problems, it's assumed that your acceleration, A, is constants. So in most of physics, your acceleration is constant. If your acceleration is not constant, these equations won't work. So your acceleration needs to be constant or average, right? If you're not told otherwise, you will assume that your acceleration is constant. So what I want to do real quick is show you these equations. I have a particular list that a sequence for them, and I'm going to list the easiest one first, the easiest one to sort of play with, to manipulate, and the hardest one last, easiest to hardest. Because if you want to try multiple ones, you're going to start with the first one. So this is V equals V initial plus AT. This one is V squared equals V initial squared plus 2A delta X. And this one is X equals X initial plus V initial T plus half of AT squared. And the third bonus one is delta X equals V initial plus V over 2 times time. I'm not going to get into how these equations come about. Your book might derive that. It doesn't matter. You just have to know how to use them. I do want to show you one thing about these equations before I kind of get into this part of the chart, which is that this equation here can be rewritten, and I'm going to call this equation 3, I don't know, B or whatever. If I move this X initial to the left, I get X minus X initial. That's delta X, right? So I can write this as delta X equals V initial T plus half of AT squared. There's less stuff if you do it that way. This is usually how I'm going to write this equation. Most of the time your initial position is 0 anyway, so it doesn't matter. Okay? Now, if you look through all these equations and you kind of make a list of all your variables, you're going to see that there are 7 total variables. But these two guys really are, they just form delta X. Delta X is X final minus X initial. And since I'm using delta X here, and delta X here, and delta X here, I'm going to consider that these 5 here are the 5 main variables. So I have 5 variables. A very important thing to know about these problems is that to solve any kinematics motion problem, you're going to need 3 out of 5. And I need you to remember that. Hey, that's cheesy. So you need to have 3 out of 5, okay? Every motion problem is going to have a little storyline. The zebra's running, the lion's coming, some stupid like that. And you need to extract 3 out of 5 variables out of the text. If you can't find 3, you're missing something most of the time, okay? So what I want to do now is show you how these equations have sort of different combinations of variables, and depending on what you have, you're going to pick different equations. And I'm going to show you an easy method to pick those. So this equation, I'm going to do this real quick, has V initial, V final, acceleration and time. It doesn't have delta X. So I'm going to put a little sad face here. This one has V initial, V final, acceleration, delta X, but it doesn't have time, sad face. This one has these two guys, therefore it has delta X, it has V initial, it doesn't have V final, sad face. It has acceleration and time. This one has delta X, V initial, V final, time, but no acceleration. Okay? Notice that every equation is missing something except that all of them have V initial, right? I'm going to talk about that first. If you have a situation where, for example, you're not being given V initial, something's missing, these equations just seem not to be enough, you can always just use a combination of 2 equations, right? So you can find one other variable and then solve it using one equation, find one variable, and then now you have enough information to use another equation and find what you need. At the end of the day, a lot of physics questions are just about hustle. You just have to, you have all these equations, just plug it in, keep going at it. But I will show you a more systematic way of doing this. Okay? Now, before I talk about how to pick your equations, there's basically 3 ways. I want to show you what happens with all of these guys if your acceleration is 0. Remember, we're talking about problems where acceleration is not 0. It's a more complicated problem, but we just had mentioned how it's much simpler if acceleration is 0. So let's look at this equation here. If acceleration is 0, and try not to make a mess on your notes, I'll make a mess here, but I'll delete, I'll go back. So this is gone. So I have V equals V initial, And so that's kind of silly, because if there's no acceleration, that means that velocity doesn't change. So this equation doesn't really tell us anything. It's useless, right? It doesn't give us any new information. Velocity final equals velocity initial. We knew that. Here, same thing happens. This cancels because A is 0, or if A is 0. And then I just get that V squared equals V initial squared. Again, useless. The third equation is going to cut out this guy here. So let me write this: x equals x initial plus vt. So that's not necessarily useless. In fact, I want to point out that this equation is the same as this one, which was an equation where acceleration was 0. They're the same equation. They just kind of simplify from one to the other. So I'm going to call equation number 3 over here our position equation. Okay, I'm going to kind of put this here. Equation 3 is our position equation. So there are two versions of the position equation, this one and this one, but it's actually the same exact equation. You can always start from here, from number 3, and then if you have no acceleration, you can just do that. And that's my point with doing this, right? I don't want you to think that for some problems you get this, and then for some problems you get this. These 4 equations always work. Except that if your acceleration is 0, you just cross it out. And then the equations simplify. Some of them will become useless because they won't really be able to help you. They'll just tell you the obvious. Some will be useful. Okay? So this equation here has no A, but even that equation works as well. And I can show you that real quick. If you have no acceleration, these two guys are the same. So I can just call this V, and I can say V plus V is 2V divided by 2. That 2 cancels, and I have a T. Delta X equals VT. If you move it around, you have V equals delta X over delta T. Okay? I'm just kind of playing around with these to show you, get you guys a little bit more comfortable with it. So that equation still works. It just kind of becomes V equals delta X over delta T. And guess what? That is this guy over here. Okay, let me just kind of do some color coding here. Looks pretty. All right, so how do you know which equation to use? People struggle with this, right? So there's sort of the brute force approach. Don't know, try all of them. And that's why I list them 1, 2, 3. I'm going to show you how to do it in an easier way, but let's say you forget. Well, just do all of them, right? Until you get something. Try the first one first because it's easiest, and then wait for the last one. Do the last one last. Now, the third one is hardest because it's got more things in it. It's got a square, but also sometimes you might get a quadratic equation out of it. It's the more tricky one, potentially a quadratic equation. That sucks, but it's also the most useful one, right? So that's kind of messed up. First way you're going to do it, try everything, right? And then that's always going to work. The second one is kind of obvious, an obvious instruction set, which is, first of all, the equation must have your target variable. For example, equation number 2 doesn't have time. It's missing time. So if you're looking for time, you can't use equation number 2. I don't care what you put in there. Time's not going to come out of it. It's not there. And you have to, not only must be, your target variable has to be there, but it has to be the only unknown. So if I'm looking for time here, but I don't have A, then I'm stuck with 2 variables. That's not good either, okay? So these are sort of the 2 obvious points. There's a third way, and that's my favorite, and we're going to use what I call, let me write this out first and I'll explain what I mean. We're going to have what I call the ignored variable. The ignored variable will determine the equation. So first of all, what I mean by the ignored variable, all of these problems, there are 5 variables and you need 3, right? You need 3 out of 5. Needs 3 out of 5. Well, all of these problems will give you 3, ask for 1, and they will ignore 1. In other words, they won't give you that value and they won't ask for it either. For example, I give you delta x, vi, v final. I ask for a. My ignored variable is t, right? It's the one that, I'm gonna put a little sad face here. It's the one that I didn't give you and I didn't ask you for. I just don't care about t. So I'm going to use, if t is my ignored variable, I'm going to use the equation that ignores t, that doesn't have t, equation number 2, okay? So if t is ignored, I'm going to use equation 2 because it's the one that ignores t, okay? So let's do some problems real quick and then you get the hang of it. A car, again, I need 3 out of 5. A car starts from rest and moves with a constant 5 meters per second squared. You need to know that this is an acceleration, okay? The method that I'm going to use to solve these problems is very straightforward. I call this listing. It's silly, but it helps. Listing your children, right? I just completely made it up. Don't quote me on that. And basically what I'm going to do is you have 5 variables and you want to make sure you don't lose track of anything. So I'm going to list them, right? So you got 5 kids now. V initial, V final, A, delta X, delta T. And the reason I'm doing this is just to get our work organized and so we can have one systematic way of solving all these problems. I need 3 out of 5. Once I have 3 out of 5, I'm good to go. Starts from rest means that the initial velocity is 0. A constant velocity of 5. And look at what A is asking here. This is part A. It's saying find the speed after 15 seconds. I'm telling you that delta T is 15 and I'm asking for the speed. Now with speed you have to be tricky, you have to be careful because there are 2 speeds. Which one is it asking for? Well, it's asking for the speed after 15 seconds, so it's asking for your V final. Another way to figure this out is that your V initial, you already have it, it's 0, right? So that's what I'm asking for. Notice how I have 3 values. I'm asking for V, and delta X is neither asked nor given, so I'm going to put a little sad face there. Delta X is my ignored variable. So go to the table and look at the equation that doesn't have a delta X. The equation that doesn't have a delta X is the very first one. Obviously you're not going to have this table during the test, but you should have the equations whether it's given to you or you're going to have to memorize them. And just by looking at these equations you can quickly see, look at the first one, there's no delta X there, right? So this tells me that I'm going to use equation number 1. Now these numbers are numbers that I make up so that I have in a certain sequence. Professors will use different orders of equations, it doesn't matter. But when I say 1 is like my version of equation 1, right? So V equals V initial plus AT. Initial velocity is 0, acceleration is 5, time is 15, and this is 75. And the units obviously meters per second. I want you guys to do part B. Very similar process. I want you to list your children. The variables are here. And then I want you to plug in all the numbers. So pause the video and try this out. You need to be good at this. I'm going to keep going. Your initial velocity is still 0 because it's still this part of the problem, but now it's jumping to part B instead. So your initial velocity is still 0. Final velocity, acceleration is still 5. Delta X, delta T. Look what it says. I want the distance, that's delta X, after 20 seconds, that's 20. I know 3 variables, I'm good to go. Now notice how the question is asking for distance, not displacement, but it's okay because we're going to solve using distance, displacement, but we know that it's actually meaning distance. Notice how these equations all have delta X, distance, displacement, not distance, and they all have V, velocity, not speed. We don't have to memorize them with different letters for different situations. So I just know that this is actually distance. Here, we're going to assume we're just moving to the right, so it doesn't matter direction. It is not an issue here. The variable that's being ignored is V, so I'm going to put a little sad face there. And then I just have to use the equation that doesn't have a V final. And if you look through your equation list, it's the 3rd equation. So delta X equals V initial T plus half of AT squared. Your V initial is this. So half acceleration is 5 time is 20 squared. If you put this in a calculator carefully, you get 1,000 meters. You get 1,000 meters. Okay, so anyway, that's it. This is the foundation of kinematics. You have to practice this and get pretty beast at it. All right, so we're done for this one.